In the world of physics, there are numerous phenomena that seem counterintuitive at first glance, but once explored in depth, they reveal the complexity of natural processes. One such phenomenon is the Mpemba effect, where hot water freezes faster than cold water under specific conditions. While this may seem paradoxical, after all, logic would suggest that cold water should freeze more quickly than hot. This effect has intrigued scientists, philosophers, and curious minds for centuries. The effect is named after Erasto Mpemba, a Tanzanian schoolboy who, in the 1960s, observed that hot water could freeze faster than cold water, an observation that led to the formulation of what we now refer to as the Mpemba effect. The story of the Mpemba effect begins with a seemingly simple question: why does hot water freeze faster than cold water in some conditions? The answer to this question is still debated among scientists, as there is no single universally accepted explanation. However, several theories have been proposed to account for the phenomenon, each offering a different perspective on how heat, evaporation, and other factors might influence the freezing process. One of the most widely discussed explanations for the Mpemba effect is that hot water evaporates more quickly than cold water. Evaporation is the process by which liquid water turns into vapor, and it occurs more rapidly when water is heated. When hot water is placed in a freezer, it loses mass through evaporation, leaving behind a smaller volume of liquid to freeze. With less water to freeze, the process is faster, potentially causing the hot water to freeze more quickly than the larger volume of cold water. This evaporation theory suggests that the key factor in the Mpemba effect is not the initial temperature of the water, but the volume that remains to undergo freezing. Another proposed explanation for the Mpemba effect involves the formation of a frost layer on the surface of cold water. When cold water is placed in a freezer, it tends to form a layer of frost on its surface, which acts as an insulator, preventing the cold water from losing heat as efficiently. This frost layer slows down the cooling process, making it harder for the cold water to reach the freezing point. On the other hand, hot water, which has already been heated, may not form as thick a frost layer, allowing it to lose heat more rapidly and thus freeze faster. This theory highlights the importance of heat transfer and insulation in the freezing process, suggesting that the interaction between the water and the surrounding environment plays a crucial role. In addition to evaporation and insulation, the concentration of solutes in water has also been suggested as a contributing factor to the Mpemba effect. Water often contains dissolved gases, such as carbon dioxide, which can influence its freezing behavior. Hot water, due to its elevated temperature, may release more of these dissolved gases compared to cold water. As hot water cools, the reduction in solutes can cause a change in the structure of the water, making it freeze faster than cold water that still retains a higher concentration of dissolved gases. This theory points to the chemical composition of the water as a key factor in the freezing process, with variations in solute concentration potentially affecting the speed at which the water transitions to ice. Another possibility that has been explored is the role of supercooling, a phenomenon where liquid water is cooled below its freezing point without actually turning into ice. Supercooling occurs when water remains in a liquid state despite being colder than its normal freezing point. This is more likely to happen with very pure water, which has no impurities to trigger ice formation. Cold water, especially if it has been slowly cooled, can become supercooled and resist freezing. Hot water, on the other hand, may not supercool as easily and may freeze more quickly once it reaches its freezing point. This theory suggests that the Mpemba effect could be related to the different ways in which hot and cold water behave under the same freezing conditions. Despite the various theories, the Mpemba effect remains a subject of ongoing research and debate. Some scientists have conducted experiments in an attempt to replicate the effect consistently, but the results have been mixed. In many cases, the Mpemba effect is only observed under very specific conditions, such as particular temperatures, container types, or initial water volumes. The phenomenon does not occur universally, and scientists have struggled to identify a single factor that can explain why hot water freezes faster than cold water in some situations but not in others. It is also worth noting that the Mpemba effect is not limited to water alone. Similar phenomena have been observed in other liquids, such as alcohols and certain solutions, under specific conditions. However, water remains the most well-known substance for demonstrating this counterintuitive behavior. Likely because of its unique properties and its relevance to everyday life, the Mpemba effect has profound implications for our understanding of thermodynamics, the study of heat and energy transfer. It challenges the conventional wisdom that colder substances freeze faster, offering new insights into how heat, mass, and molecular interactions can influence the freezing process. The mystery behind this phenomenon also underscores the complexity of nature's behavior, reminding us that the world around us is often more intricate than we might assume. In conclusion, while the Mpemba effect remains an enigma in many ways, it serves as a testament to the wonders of scientific inquiry and the ongoing quest for understanding. Whether it's the rapid evaporation of hot water, the formation of frost layers, or the unique solute dynamics at play, each proposed explanation offers a glimpse into the intricate and often unpredictable nature of the physical world. As researchers continue to study the Mpemba effect, they may one day uncover the definitive reason behind why hot water sometimes freezes faster than cold, shedding light on a phenomenon that has intrigued scientists for decades.